So we've calculated the electric field of a simple charged rod, a little one-dimensional length of charge. And we calculated the field on the end and then off to the side. And those problems get harder when you get into different shapes of charge. And when you get into different shapes and curved surfaces, you have to really be careful what coordinate system you use. So let's do continuous charge in more dimensions and coordinates. So here I'm going to show you how to start, where you find the DQ for different kinds of problems, and then we'll do one. So first of all, you can have more than one kind of charge density. So we already did linear charge density, which we write as lambda, and that's charge per unit length. That's linear, so that's in coulombs per meter. That's how we did the rod. We gave it a certain charge per unit length. You can also, though, have a surface charge density. And that's what you might expect. Its symbol is sigma, and it's just the amount of charge per meter squared, the amount of charge per unit area. But how you do problems with lambda and sigma kind of depends on the problem. So one way is to go with Cartesian coordinates, which is just a fancy name for the standard xy coordinates. So if we're going to do a linear problem in Cartesian coordinates, then you really just need one coordinate. You just need x. And it's just like before. We put it on the x-axis. We put plus x that way and minus x that way. We put the origin in the middle. But the key was this line of charge had a charge density lambda, and we just said dq is, when we had to treat this as a little individual charges, we had a little length dx, so dq was just lambda dx. And we set up the integral from there. So now, let's see, what if we were faced with a surface charge? We might be given a square with charge density sigma. Well, if you're going to treat a square in Cartesian coordinates, which of course is the way to do it, is you might say we'll put one side on the y-axis and one side on the x-axis like that. And then you still need a differential element. Well, now in 2 dimensions, the differential element is a differential area. Okay? So in this case, the area would also be a little square like that. And its size is based on a little differential dx in the x-axis, this is getting small, and a little dy in the y-axis like that. Okay? So we would just divide this up into a little differential area. So then the dq, in this case, it's sigma times dA. Same basic idea, you just take the charge density times the area dA. But now we want to translate dA into the actual coordinate system. So we say dq is sigma times dx dy. Because our little dA is just a little square, or a rectangle, where one side is dx, one side is dy, so the area is just dx dy. Okay? So in Cartesian, that's how you would set it up. You may also want to use, for some problems, polar coordinates. So these are usually given r theta. Okay? And you can have problems that are still 1D charge, linear charge density, but in polar coordinates. And the example is this. If you have essentially a line of charge or a thin rod of charge that's bent into a semicircle, so say it comes down like that, and then this also goes around like that. And you're still just given lambda. It's still lambda equals the total charge on this rod divided by the length, which in this case would be half of the circumference of the circle. So this you would also treat in polar coordinates. And what you'd do is figure out where to put everything. You'd put the origin here. And the way polar coordinates work is you have some angle you kind of define as 0, so it could be straight up. And then when you go to a point in space, you define it by how far you went out in terms of the radius. I've got to distinguish my r's and my sigmas here. How far you went out in terms of the radius and how far you went from angle 0, and you call that theta. So it's r and theta is how you define this thing. Okay? Now, we have to get to a differential element. So a differential element is a little piece of this thing. So just like we had a piece of the linear charge here, dx, here we need this little piece. And in the end, dq is lambda times the length of that piece. Now in polar coordinates, the length of that piece is r times how much you changed theta. Right? So when you're going along this curve, r doesn't change. So it's r d theta. R d theta is a length. Theta doesn't really have units, r has units of length. So that's your dq if you're doing a linear charge density on a curved surface. Now, what about a surface charge density on a curved surface? Or in this case, we would do a round surface. So I'm out of room here. So let me do it here. Okay? So the curved surface you would probably deal with is a disk. Let's imagine we have a disk of charge. It's kind of perpendicular to the board is how I'm trying to draw it here. And it has an origin, and it has some charge density, sigma. Okay? And you have to calculate the electric field somewhere. Doesn't matter where. What we have to do is break it into a differential area, just like we did that square. So dq would be sigma, the charge density, times dA. So it's just how do you draw a dA on this circle? So what you do is you're going to have to vary r and theta. Okay, so let's say you come out here. This is r, and again, this is theta. Okay, so let's pick a little differential area. What you have to do is you have to come out to a certain r and stop, and then go a little bit farther. This is r, and then this is r plus dr. You've moved a little dr right there. And then you sweep that through a little angle, and you do it again. R and r plus dr. So this is dr, and here you've gone d theta right in there. And then you know this little length is r d theta. That's the length of an arc. Whoops, the length of an arc like that. So if you want the area, you think of it as a little square, and the area is just r d theta times dr. So dq is sigma times that area. R d theta is this length, dr is that length, but we often rearrange it so it sounds nicer. R dr d theta. But really what's making the area is r times d theta is one side, dr is the other side. Okay? And when you write this, you got to be very careful that your r's and your sigmas can be distinguished. The way I normally write, they look similar. So I got to be careful when you're doing these kinds of problems that you don't mix them up. Okay? So we can keep going here, and now what we can think about doing is a problem where we actually calculate the electric field. But I see we have a question first, so let's go back before we keep going and see what this question is, and it is KT anomaly. What about 3D? Yes, of course, you can have 3D. So we would call that a volume charge density. So let's just add it to our table here, volume. And in that case, we call it rho, and it would be in coulombs per meter cubed. So charge per unit volume. If we wanted to define a volume element, we have to pick a coordinate system. If you wanted to continue in Cartesian coordinates, you would just add another dimension. So dq, your charge element, would be the density, rho, times the little volume dv, which is just in Cartesian dx, dy, dz. If you think in terms of the angular coordinate systems, you have, in 2D we had cylindrical. So if you want to take that to 3D, all you have to do is add a z-axis to it. If we look at our circle here, our polar coordinate system, if we just add z, then you can imagine this little area we talked about before and just have it come out in dz. So in that case, we could do this in what would be cylindrical coordinates. dq would be rho times r dr d theta, dr, r dr d theta, that's the area, and then we just add dz. And that would turn it into a volume. One more option you have for 3D would be spherical coordinates. Those are more difficult. There you have a radius dimension or a radius axis and then 2 angles. It gets very confusing. So most problems we do, we're going to stick with area, charge per unit area. We might do some volume, but if we do, it'll definitely be one of these 2 coordinate systems. We won't do spherical. So let's go ahead and do a problem just in 2D. We now have a way to calculate the dq for a surface charge. Let's go ahead and do it. Let's do a problem. Let's do the charged disk. With charge density sigma, radius r, and let's find the E field at a point. We're going to do a point on the axis of the disk. You'll see what I mean when I draw it. So first, let me draw the disk. Here we go. Nice, big disk. Now this has to be thought of in 3 dimensions. Okay, so this is a disk sort of in the plane of the board. Here's its center, and we're going to put its center on the z-axis coming out this way. So there's the z-axis. We can assume its origin is at the center. Okay, so we're looking for the E field at a point on the origin, or along the z-axis, point P, like that. Okay. So the first thing, like I said, is you got to think about what's your charge density like, what coordinate system you're using. So we're going to use polar coordinates. We have to find a little chunk on this disk that we can describe its dq. So what we're going to think about is some point here on the disk at a radius little r. Okay? So in this case, the total radius of the disk is big R. Often we'll use big letters to mean that's the total, and we use the little letter to mean that's the one that we're going to vary. So there's 2 R's in this problem. There's big R, which I don't want to draw because it'll make the drawing messy. Big R is the radius of the entire disk. Little r is this one that I'm moving around. Okay? So we're going to go and say this is r, and then we're going to move up a little bit and say that's r plus dr right there. So r to r plus dr. And then we're going to move in theta. We're going to go from this point theta to a little point going over theta. So we went r plus dr, and this is theta, where theta would be measured from here. And then we went over to theta plus d theta. Okay? When we do that, we set up a little area. This is our little dq. Okay? Just like we drew it big before. So that's the charge we're going to deal with. Okay? Let's think about the field it's going to create at P. Okay? So first, let's say we now have our charge dq is, like we showed before, sigma r dr d theta. There it is, right there. This is going to make a field. But now, here's the key. We have to use symmetry. Okay? What is symmetry going to tell us? What you have to visualize and think about is the fact that this charge is making a field here. Let me make the z-axis longer to get it out of the way. Okay? So let's think about the dotted line coming all the way from that charge through that point P. We know that it's going to make a field sticking off the z-axis at some angle, like that. Okay? And actually, in this case, it's even more complicated. It's going kind of into the board. All right? But we also know that somewhere else around the sphere, or around the disk, is another charge that would make one pointing like that. And this would make one pointing down, and this would make one pointing up. And those would all cancel. This component of the field for all these different ones would cancel. And you'd only be left with a z component. Okay? So use symmetry, and what it tells us is all non-z field cancels. So when we do this calculation, we only have to consider the z component. So now we need to go through and think about this angle right here. Oh, okay, so we have a question here. Let me pull this up and see what we got here. Spatially challenged. I need to see it in the VisLab. Okay, so that was a very complicated drawing I did. Okay, let's go look at it in the VisLab and make sure you get it. Okay, spatially challenged. Here is the charged disk in gray. We're looking straight onto it. And as you know, we can move out the charged disk in the radial direction, we can move around the charged disk in the theta direction. That's why this little dA is r d theta times dr. So there's your dA. And that's also your dq. It's equal to dq is sigma times dA. So if we think of that as a point charge, we want to know the field it creates on an axis normal to the disk. So if we spin this thing around, then you can see this. So now here's the axis. We wanted the field at some point P, normal to the disk. So here is dq, here's point P. The field it makes is along that axis. So there's dE. That's the differential element of the field. It's at an angle phi with respect to this axis normal to the disk. So this angle phi has nothing to do with the angle going around in theta. The angle that you get here, phi, actually depends on how far you are out in radius. Okay? So there are two angles, and there's a lot of geometry to keep up with. All right, let's go. Okay, so hopefully that helped. So hopefully that helped you see that this complicated component is sort of sticking off into space, but it'll always be canceled. All we really care about is this component along Z right here. Okay? So the angle between the actual DEP and DEPZ, the one we need, is we're going to call phi. Okay? We can't call it theta. It's not the same as theta. Theta is going around this way, and phi is going around the z-axis. They are different. Okay? So let's see if we can take all that and successfully write the DEP. Let's see. Okay. Coulomb's law, essentially. Ke, Coulomb's constant, times the charge, and I'm going to go ahead and write it this way. Sigma r, don't mix your sigmas and your r's, dr d theta. Okay? So that's dq, that's the charge. And now we need it over the separation squared. So we need it over this line right here. Well, fortunately, that is a right triangle. From here, the dotted line, to this solid line right there, that is actually a 90-degree angle. Between the z-axis and r is 90 degrees. So we do have a right triangle to use where the hypotenuse is going to be the square root of r squared plus z squared, because we're at a point P along the z-axis at a distance z away. All right? So it's getting a little messy in here, but this is r, this is z, therefore those two, or therefore the hypotenuse is the square root of r squared plus z squared. And we need to square it in the bottom. Okay. So there's the bottom. And now we need the z component. Okay? So to get the z component, well, it's like there's some this way, there's some down. It's the cosine of this angle. It's the adjacent, and there's the hypotenuse. So cosine of phi. All right? So that gets us all the way down to that. And then the direction is all we need. Since we called it the z-axis, I'll call it k hat. All right? So there, we've successfully set up the DEP. Now we just have to do the integral. We have our DEP. Now we just have to integrate to get the field. So let's integrate. Let's say that EP, the thing we want, the E field at point P, is the integral of DEP. We're just adding up all the DEPs. And that's the integral of this. But there is something special here. When we have a sigma, that means we're doing two dimensions. We have a two-dimensional charge distribution, which means we have two differentials here. Of course, we have to integrate over 2 dimensions for a two-dimensional thing, which means it's a double integral. We have to actually have two sum symbols. One is for dr, and one is for d theta. Okay, we'll work on their limits in a minute. For now, let's just go ahead and write it. We have Ke. I'm going to start pulling some constants out. Sigma is here, and then this is r dr d theta. And this is r squared plus z squared. And we never dealt with the cosine phi. Let's think cosine phi from that drawing. Cosine's adjacent over hypotenuse. Adjacent was z, so there would be a z in here. Let me fit it in here. And then the hypotenuse was the square root of r squared plus z squared. So there's another one of these in the denominator, which brings that to the 3/2, if you will allow me to skip a step there. So that's our integral. These two apply to these two, so let's think about the limits for this disk. If we're going to represent the entire disk, we have to integrate the radius from 0 to r, so that can be the radius integral. And if we're going to get the whole disk, we have to go all the way around the circle, so theta has to go from 0 to 2 pi. Okay? So there's our integral. Let's look at it. When you do these two integrals, you just do them separately. You just do them one at a time. So in one step, we can do the d theta integral. If all you have is integrating d theta from 0 to 2 pi, the integral of d theta is just theta. And when you evaluate that from 0 to 2 pi, well, theta at 2 pi is 2 pi, minus theta at 0 is 0. So this integral just becomes 2 pi. Okay? So let me just write it as 2 pi as part of the constant. So the 2 pi is the theta integral. And then you still have a ke, and you have a sigma. And actually, z is a constant in this case. Z was just how far out are we. So there's really, that's not changing as we move around the disk. So there's our constants, 2 pi, ke, sigma, and z. And we're left with this integral from 0 to r of what? R, and I'm going to write it like this. R times r squared plus z squared to the minus 3 halves. Go ahead and just not write it as a quotient, dr. Okay. Similar to how I did that integral when we had the point charge near the rod. We'll just write it this way. Okay, so if we keep going then, EP is, let's keep our constants, 2 pi ke sigma z. And if we want to integrate this, this one's actually doable. Minus 3 halves becomes minus 1 half. You divide by that, that becomes minus 2. And then you also divide by the derivative. You divide by 2r. The r goes away. So you're also multiplying it by 1 half. Doing that again. And then it becomes this to the minus 1 half. Right? R squared plus z squared to the minus 1 half. I like doing these integrals better writing it out this way than having the square root things in the bottom. It just depends on how you want to do it. And that's evaluated from 0 to r. This is 2 to the minus 1 half, evaluated from 0 to r. Okay? So we can simplify a little bit. Those 2's go away. It leaves a negative sign sitting there, which is along for the ride. So E, and of course it's on the k direction. So EP equals, let's keep our constants as many as we can out, 2 pi ke sigma z. And those 2's went away. We pull the negative out like that. And now we plug in big R into the little r. So that becomes 1. I'll go back to quotients now. 1 over big R squared plus z squared minus, and now we plug in the 0 for the r, minus 1 over the square root of 0 plus z squared. Oh, that's just z. Once the r goes away, it's just the square root of z squared, so that's just z. In the k-hat direction, because of symmetry. And, you know, we can make this look a little simpler. I guess if we pull the negative in, it'll switch sides, and these two will switch sides, and we could carry in the z to make that be a 1 and put a z up there if we wanted to make it pretty. I think it's beautiful as it is, but if we could clean it up a little bit, sigma, it might look like this. Pull in the z, 1, switch the order by getting rid of that. 1 minus z over the square root of r squared plus z squared. And that's probably about as simple as you'd want to bother to make it. Okay. So there you go. That's a case of doing a disk. There are different kinds of problems you could do. That's sort of the most straightforward disk problem that we can come up with.